Welcome back, students, to Unit 9 Solutions. Today we'll be talking about the different units of concentration and how to perform a dilution, Unit 9.2. When we talk about chemicals in this class, specifically solutions, we care a lot about what's in them. If I have a beaker and it's clear, you should never assume it's water. Most likely there is something in that water, and you're going to want to know what it is. So some substance, like say it's sodium hydroxide, is in that solution. How much really matters. So we keep track of how much by talking about its concentration. How much of your solute do you have in your solvent? So there are lots of different units of concentration, and in the end it just boils down to how much stuff you have in a set amount of space. So the most simple form of concentration that you need to know for this class is molarity, symbolized by the variable capital M. Capital M, molarity, is the moles of solute for each liter of solution. Now, granted, a liter is a lot of substance, so most of the time in this class, I'm going to give you milliliters, and you'll have to convert that to liters. Another thing of note is that we cannot measure out atoms of stuff. Knowing the moles of solute is going to be very difficult. Most often, you'll be given a gram amount, and you're going to have to convert that to moles in order to do these problems. So let's just hop right into it. Find example 1 in your packet. What is the molarity of a solution of 100 milliliters of water and 36 grams of hydrochloric acid? Hydrochloric acid we haven't covered yet. How to name acids. Hydrochloric acid would be HCl. So with 36 grams of hydrochloric acid, 100 milliliters of water, we're asked to find the molarity. Well, molarity is the moles of solute, the thing you have less of, divided by the liters of the solution. So the thing we have less of here is the hydrochloric acid. So we need to know how many moles of hydrochloric acid you have, because that's going to be our numerator for our molarity. So to do that, we'll set up our factor label method. If I have grams, I want to get rid of grams and end up with moles of hydrochloric acid. We use the molar mass, the number of grams in 1 mole. So the molar mass of hydrochloric acid will go here, which is 1 hydrogen and 1 chlorine. So that's 1.01 plus 35.45, that's 36.46. Giving us approximately 1 mole of solute. The next part of this problem had us tackle our denominator, our liters of solution. If we have 100 milliliters of water, we're going to dissolve our hydrochloric acid in it. Let's assume that the hydrochloric acid has no volume. It's a bit of an assumption, but that means our liters of solution here is just of the water. We need to convert from milliliters to liters. For every 1 liter, there are 1,000 milliliters. So milliliters cancel out. We have 0.1 liters of solution. So our molarity comes out to be 9.98 molar hydrochloric acid. It's good practice to put what the solute is, because that's the thing we are interested in. The next problem had us go the other direction. If I have half a molar solution of sucrose, how many grams of sugar are present? So molarity is the moles for each liter. If I want to know how many grams are present of our solute, I can find that out by figuring out how many moles you have. Because once you have moles, you can convert moles into grams. So this problem is going to have us work backwards. If we want these moles, we can multiply by our volume on both sides. So molarity times volume gives us the moles of the solute. So if we take our volume and we multiply by our molarity, we can get the number of moles. So 0.5 molar times 500 milliliters can't go here. We need the number of liters. So we'll take 500 and divide by 1,000 to get rid of milliliters to get 0.5. There's a quarter of a mole of sucrose here. So we'll take that quarter of a mole and we'll multiply by the molar mass to get rid of moles and go to grams. So the molar mass of sucrose would be 12 carbons and 22 hydrogens and 11 oxygens. So that'd be 12 times 12 plus 22 times 1 plus 11 times 16. The molar mass of sucrose is 342. So a quarter of that would be 85.5 grams of sugar is in our half molar. Molarity is the concentration unit to know. Your SOL will test you exclusively on molarity for concentration. So your first 7 note quiz questions deal with molarity. You can pause the video and complete note quiz questions 9.2, 1 through 7. When it comes to making these solutions, the way that a solution is made is that we take our solute and calculate how many grams of it we need, and then we mass that out on a scale. We put it into a volumetric flask and then dissolve it. Once it's fully dissolved, we can fill the volumetric flask to the final volume of the solution. The reason we do this is because the solute does have a volume of its own. So by dissolving it before you take it to the final volume, you account for that. So if you're ever asked on a quiz, hint, hint, how to make a solution, you measure out the mass of solute needed, you dissolve it, and add enough water to reach the final volume of the solution. Which brings us to your practice for the day. Please do page 8 through 10 in your packet. You can skip number 6 and 8 on page 10. Molarity is not the only unit of concentration because molarity is subject to change. If I heat up a solution, the solution expands. So if the volume increases, this will cause molarity to decrease. So when we have a solution that changes temperature, we don't really use molarity because it will change depending on the temperature of the solution. So instead, we look at molality. Molality, symbolized by a lowercase m, is the moles of solute for each kilogram of solvent. This causes us to negate the whole temperature changing the volume, and it's based off of mass. That's why throughout the year we've used lowercase m to symbolize mass. This will help you hopefully remember molality is based off of mass. Also, molality has 2 L's in it, like mass has 2 S's in it. So a molality problem would be example 2a in your packet. What is the molality of a solution made from 100 milliliters of water and 5 grams of sodium chloride? Sodium chloride is going to be our solute. So we are going to need how many moles this is. So 5 grams of sodium chloride, we have to convert this into moles. Again, we'll use the molar mass off the periodic table for sodium chloride, which would be 1 sodium, 23, and 1 chlorine, 35.45. The molar mass is 58.45, which means that 5 grams represents 0.086 moles. Now that's for every kilogram of solvent. Our solvent here is the thing you have more of. We have way more water. 100 milliliters of water, since water has a density of 1 gram for each milliliter, means that we have 100 grams of water. And there are 1,000 grams in every 1 kilogram, so we have 0.1 kilograms of water. So if we divide 0.086 by 0.1, we get the molality of this solution being 0.86 molalol sodium chloride. Another different unit of concentration we do a lot with gases. In the last unit, we talked about how the air around you is 16% oxygen, but if you looked at that formula a little closer in your packet, you saw me list actually the mole fraction, which is the moles of a solute for the total moles present within a solution. So mole fraction is simply the moles of solute for each total moles present, which would be the solute and the solvent. So, for example, 2B, what is the concentration of 0.4 moles of benzene and 1.6 moles of naphthalene? We have 0.4 moles of benzene in 1.6 moles of naphthalene. So if we add the two together, that's 2 moles total. So the mole fraction of benzene would be 0.2. Mole fraction is symbolized by the Greek letter chi. It's like a fancy X. Another commonly used unit of concentration is the percent by mass. That's what we use most often in the real world. Percent by mass is simply the mass of the solute for the mass of the solution. So if something is 10% sugar and you have 250 grams of it, if I want to know how much sugar is actually in that solution, I can simply take 10% of 250, 10% of 250 to get that there are 25 grams of sugar. Mass percentage is actually what your parts per million are based off of. Parts per million is simply the mass of your solute divided by the mass of your solution times 1,000,000. So if I have 20 grams of salt in 100 grams of water, that means I have 100 grams of water and 20 grams of salt for a total mass of 140 grams. 20 divided by 140 is 0.14 times 10 to the 6th is 143,000 parts per million. The SOL will only ask you about molarity. So if you are comfortable with molarity, you're going to be fine. However, on my test, I'm going to expect you to know these other units because I'm crazy and I expect you to be able to do real-world chemistry with parts per million and molality, which will come into play in the next subunit. Because when we talk about concentration, sometimes we have to do a dilution. If we have too much solute in a set amount of space, we can spread it out by adding more solvent. This will lower the concentration by increasing the volume. Molarity is the number of moles for each liter of solution. If I increase the volume, the molarity goes down. So we can make things more diluted. Dilution formulas work off the idea that the amount of the amount of solute doesn't change. So the moles of solute always being the same means we're just going to change the volume. It's a pretty straightforward formula. The molarity and volume of your concentrate has to equal the molarity and volume of your dilution, where the dilution's volume is your final volume of solution. Like at the end, how much were you trying to make? We do dilutions by taking that volume of concentrate, putting it into a volumetric flask, and adding water to the volume of the dilution. Because the molarity of your concentrate is going to drastically fall once you add more solvent. So find example 3 in your packet, which has lots of problems. So first off, what volume of 3 molar potassium iodide would you use to make 300 milliliters of 1.25 molar potassium iodide? So, the molarity of our concentrate times the volume of our concentrate has to equal the molarity of the dilution times the volume of the dilution. This question says I have 3 molar, which is way more concentrated than 1 molar. So this is my dilution. In the end, my dilution has a volume of 0.3 liters. This question wants to know what is the volume of the concentrated solution. So to get the concentrated solution by itself, I'll take the concentrated molarity and divide on both sides. So the volume of the concentrate is going to be the molarity of the dilution times the volume of the dilution divided by the molarity of the concentrate. So we can plug in 0.3 liters times 1.25 molar over 3 molar. Molarities cancel out and I'll be left with liters. I would need 0.12 liters of my concentrated solution. So I would take 0.12 liters of the concentrated of the 3 molar concentrated solution, and as I add water in, this concentration's gonna drop down to 1.25 molar once it reaches a final volume of 0.3 liters. Second verse, same as the first. How many milliliters of 5 molar sulfuric acid stock solution would you need to prepare 100 milliliters of 0.25 molar? Question 2 has 2 parts. First off, we're asked to figure out the volume of the concentrate we'll need to reach a final dilution, and then how much water do we have to add in order to get to that value. So let's tackle this one at a time. How many milliliters of 5 molar sulfuric acid solution is needed to prepare 100 milliliters of 0.25 molar? 0.25 is way less than 5. So 5 must be my concentrated molarity. 0.25 is my diluted molarity. So this must be the volume of my diluted solution. If I want the volume of my concentrate, I can divide by the molarity on both sides to give me the volume of the concentrate would be the molarity of the dilution times the volume of the dilution divided by the molarity of the concentrate. The problem says that you end up with 100 milliliters of 0.25 molar and you started with 5 molar. So the volume of concentrate needed to do that, molarities cancel out, is 5 milliliters. So what this problem means is that I'm going to take 5 milliliters of my sulfuric acid and I'm going to drop it into my volumetric flask. I got 5 milliliters of 5 molar acid. And then I'm going to put water into it until I end up with a final volume of 100 milliliters, because that will reduce the molarity down to 0.25. The second part of this question says, great, how much water did you add? So it wants to know this step here. If I'm ending up with 100 milliliters and I've already got 5 in there, how much water did I add? Well, wouldn't it just be 100, the final volume, minus the 5, the starting volume? So I end up adding 95 milliliters of water. A quick side note here, If you were to do this in the lab, you would injure yourself severely. Concentrated sulfuric acid cannot have water added to it. In order to do this safely, you would do these steps slightly out of order. You would first start by adding a decent amount of your 95 milliliters. Maybe not all 95, but like maybe 70. All right, a lot of water into the bottom of your volumetric flask. And then you would put your 5 milliliters of concentrated acid in. So you would end up with something like this, like 75 milliliters of some concentration of sulfuric acid. The reason for that is that sulfuric acid boils when water is added to it. Concentrated sulfuric acid boils when water is added to it. So this problem is a little out of order. All right, never add water to acid. It's always the other way around, acid to water. Our final example problem has us solve for a molarity. If you dilute 20 milliliters of 3 molar solution to make 100 milliliters, what is the molarity of the dilution? So these are our volume of concentrate and molarity of concentrate, and for once we are solving for the diluted molarity. So I'll divide by the volume of the dilution on both sides to give us the molarity of our diluted formula is going to be the concentrated volume and molarity divided by the volume of the dilution. So we end up with 20 milliliters times 3.5 molar divided by 100 milliliters. Milliliters cancel out, and I'm left with 0.7 molar. With that being said, we are now done with Unit 9.2. You can do the last 3 note quiz questions, as well as get lots of practice on dilution problems, so number pages 11 and 12. I will see you next time, where we wrap this unit up by talking about colligative properties and different types of solutions.